Good morning, physiology friends. Again, I want to thank you for yesterday. Yeah, I know it was a co-op quiz, and I did apparently date myself by when I asked what was current and annoying, and I wasn't current anymore, but that's okay. I'm old. It is what it is. Today, our job is just simply to discuss that second line of defense. Recall the first line is really just the skin and the mucus protecting all the barriers inside or to getting inside. So the first line is keeping everything out with oil and glands and stuff and bactericides and whatever. The second line of defense is the non-specific stuff when you get when some sort of pathogen, whether it's a bacteria, a virus, a parasite, both of them, a fungi, I'm a fungi kind of thing, any foreign invader. And what I couldn't think of the other day is sometimes this is stuff that triggers in an autoimmune disease. I don't know why I got stuck on that the other day, but also similar to autoimmune stuff. And again, once you get inside, whether it's innate stuff, as we talked, that second line is kind of innate, natural stuff, or whether it's general stuff, or whether it's the specific immunity, which we'll talk about tomorrow. A lot of that is just based on cell membrane markers and stuff that your body's trying to recognize as not yours. Anyhow, last time we were talking about white blood cells that are really the only fully functional cell, and I'll skip past some of these, the only fully functional cells that are in your blood, because red blood cells have dropped their nucleus so they can carry more oxygen, and platelets have just developed into parts of things and stuff. And then we looked at these, really these 5 different types of, you can put the lymphocytes together, but these 5 different types of white blood cells and stuff, leukocytes and lymphocytes. Lymphocytes are involved in the specific immune response, but these leukocytes are monitoring, and they are general macrophages, develop into macrophages like the monocytes and stuff. The basophils, you might have heard of mast cells before. That's an allergic, oftentimes an allergy histamine thing. But these are things that basically are phagocytic. They are general stuff, and if they detect a foreign invader, they engulf them. And then, of course, they can do things, engulf them and hit them with enzymes and lysozymes and do some stuff along that line. So that was one general thing. We also talked about the immunological, I'm still struggling with that word for some odd reason, the immunological surveillance of natural killer cells. And whether that's cancer cells or, again, any other pathogen coming in. And again, similar to with markers, they recognize what is there, and again, drive them really to perform apoptosis. As we talked about, they release this perforin chemical that basically punches holes and loses the homeostasis and drives apoptosis of those cells. I got a better picture here than the one that didn't show up before. It's a little more specific, but you can see, and this is just looking at tumor cells. So here's a healthy cell, and you can see that by the markers, and especially this, the MAC class of markers, which is often one of those markers that disappears in a cell that has become cancerous. But you can see that all the markers are here, the perforins stay where they should be, and life is good. But without this marker and without this binding on a tumor cell that often will lose its MHC markers, now you don't have that binder. That says this is not right. And you can see the perforin, the lytic perforin granules get released and then do their thing. So that's part of that general immunological surveillance stuff. Now, as I wrote here, they destroy abnormal cells, abnormal daughter cells occurring during cell division, but it's not perfect. It doesn't always get everything. Okay, and again, trying to move my face out of the way if I can. sometimes tumors disguise, just like bacteria. Sometimes the macrophages, the white blood cells, don't recognize bacteria because there are bacteria that come, or viruses that will come in, and through the course of what they do, if you remember a little bit about some biology, they are encapsulated. Besides what they have, they are encapsulated, and oftentimes they use, especially in humans and eukaryotes, they use the cell not like bacteria, when viruses infect bacteria and just grow up and lyse and blow apart the cell, but they use the cell's machinery to just send out more. And in doing that, they use the Golgi apparatus and secrete more viruses. And so bacteria and stuff can kind of fool your immune system by being encapsulated and stuff. And the same thing can happen with tumors. And so you miss that detection because the markers, you've disguised the fact that it doesn't have the markers you're looking for. And so they don't have those antigens or the chemotaxis, okay, to trigger that thing. They might have some chemicals that will kill NK cells as they bind. Okay, so then they can spread and trigger other tumors. So something to think about. Nothing's perfect. Otherwise, we'd be all doing great. Okay, interferons. Back when HIV came around, one of what they hoped was a promising treatment was interferon treatments, because again, they're kind of like natural killer cells. They are proteins released by activated lymphocytes, macrophages, and other stuff. Problem is, they're just general. They're big antiviral proteins, okay? But they do try and interfere with, like I said, they don't wrap and kill and whatever. They will activate NK and macrophages to come and do their thing. But what they want to do as interferons is interfere with the replication of the virus. So back when HIV started, they were looking to find ways to make that more specific to, say, HIV. But again, it's a general, despite its coming from lymphocytes and having triggers and stuff, it's a general deal. Although there are 3 types, okay? There's alpha, beta, gamma. There's your Latin, okay? Alpha interferons produced by virus-infected cells will attract and stimulate natural killer cells, okay? All right, and give viral resistance against the virus, and try and do the apoptosis extravaganza there. There are beta that are secreted by fibroblasts. Remember, fibroblasts are, you get a boo-boo, you get a damage, you get something like that, you're going to trigger the inflammation process. And those beta interferons will be there also as a protein to help limit the infection or the entry of pathogens. And then you have gamma interferons, which are secreted by T cells and NK cells to stimulate the macrophage activity. And those T cells are part of the specific immune response. So there is overlap in how some of this works. But again, they're general overall innate responses. So while they may be triggered by certain specific immunity, because it's all working together, it's just a specific immunity takes time to trigger. They're all working together, but they were not able to specialize to get interference to specifically attack a certain virus. Okay. So here you go. You can see the different types. There's the alpha on top, produced by cells infected with viruses. They attract the NK cells. It's a chemotaxis moment of saying, come here, we're bad. The beta ones, you can see by the fibroblasts, somewhat slow down the inflammation in a damaged area and stuff. And it just gives it time to take care of any pathogens that may enter into damage. And then there's the gamma interference also. Then there's the complement system. This is, again, another, as I try and move my face out of the way so you can see everything, another protein system that, as it says, complements the antibody action. So this is stuff that will be active during the specific chemical, the specific immune response. What a complement proteins are. Oh, how do I want to say it? They're plasma and cell membrane proteins. They can be one of the terms is opsonins, which is just a protein that helps, that is part of the immune response. They're cytolytic. What do I want to say? Cytolytic agents, meaning cytolysis is similar to throwing off the osmolarity of the cell so that it may burst, so they can do that with an infectious cell. Again, opsonins are proteins that, very much like natural killer cells, will disrupt the function of an invader. They are also mediators of inflammation, somewhat like interferon, where they help regulate the inflammatory response that comes on. They have a couple pathways that are activated. The classic is the most rapid and effective, and they attach to the antibody, and that's the opsonin portion of it, already bound to the pathogen so that they help destroy it. Okay. Attached protein activates and initiates cascade to activate and attach other complement proteins. What we're going to learn or discuss as we look at specific immune responses, antibodies are great, but antibodies are signaling molecules that latch onto the pathogen and then signal other stuff to come in, like NK cells and complement, to come in and do the killing. Okay. Another pathway which takes a little longer is the complement proteins activate in plasma after coming into contact with foreign material. So similar to immunological surveillance, but not quite the same extravaganza. Okay. Again, you can see like NK cells, what are their effects? They can disrupt the punch pores into the integrity and the homeostasis. Just like NK cells, they can attract macrophages and stuff, so they can engulf mast cell release by basophils and release that histamine, which is, think of an allergic response. That's what mast cells and histamine do, which is why when you have an allergy, you take an antihistamine. Okay. And then the inflammatory response, and this is a good thing, although it doesn't always feel good. Okay. You get an infection, you get a boo-boo, you get a lot of stuff. Okay. One, in that localized area, you get a bunch of swelling. Why? Because things are rushing in there, blood's coming through. We've already talked about, how that you don't have the time with the lymph system to always pick up fluids and everything. It might be damaged so that it's not picking up things, that interstitial fluid is just like an edema forming and stuff like that. It could just be, even if it's not damaged, an infection in that area, and there's a lot of action going on and things, and so you get a lot of interstitial fluid and stuff there. Okay. There is redness in that localization. Part of it is because of the edema or the localized swelling. Part of it is an increase in the heat. Part of it is the fight and stuff like that, and things that go on underneath in the fight, and the macrophages and the cleanup stuff and all the process. Sometimes when you have an infection, you see a lot of pus. Just so you know, that's the macrophages, the white blood cells doing their action, going to war and engulfing and doing things. Of course, there's increased heat, because that is, you want to raise the temperature and try and, heat kill the infection or the any foreign pathogens. You want to denature their proteins and stuff to let them do stuff. And there's pain, and the pain comes from you're pressing on the nerve tissue as that swelling occurs and stuff like that. You're pressing on the nerve tissues, and that's why you feel the pain. You're putting the pressure on those, and that's pressurizing the nerve endings and pushing on them, and it doesn't feel good. Okay. while that sounds very simple, it is a complex process. We're not going to go through everything, but it's chemotaxis. It is just like when you got a cut and there's signals that say, oh, we got a cut and blood flow here and do all this stuff. Cells that are damaged from any source release what are called prostaglandins, proteins, potassium ions. Okay. You might see foreign proteins or other pathogens in there as the innate macrophage process goes on and stuff like that. But that's a chemotaxis trigger to say there's something going on here, infection, damage, whatever, and we need to trigger the inflammatory response. That's a big trigger of the immune system. Okay. And then there's fevers. And you've been sick and you had a fever before. And again, body temperature is right around 37 degrees Celsius. Okay. And pyrogens are just chemical substances that will jack up the heat. Now, this one we're looking at overall body. We're not talking about the localized heat and swelling of the inflammatory response, although fever is can be a part of that. Okay. But you're raising body temperature, and that's to inhibit the function of viruses and bacteria, hopefully denaturing their proteins. Okay. And it also increases, temperature is a chemical reaction rate increaser. So it does increase the metabolic rate, which will kick in the immune system, accelerate the defenses in the repair process. Okay. So that is generally your innate process is your second line of defense. So first we try and barrier anything from coming in. Okay. If it does get in, then you have the second line of chemical mediated stuff with macrophages, interferons, complement, NK cells that all try and help do the job in a general sense, but is also in concert with the specific immune system, which we'll talk about tomorrow. So anyhow, there's our good background. Listen, it's going to be a nice day out there. Make sure you get out and enjoy some of the day and take a break from staring at screens. I don't know about you, but I'm noticing a change. I have to pull away from screen time because I'm looking at it so much more often that I can tell that it has an effect on eyes and heads and stuff like that. So make sure you get out and enjoy the day after you watch this video, or after you've done another class, go out and enjoy the day and then come back. Don't care. Make sure you're taking care of yourself. Have a good day, and we will talk at you very soon.